Hello everyone, this is BB Sangmay, and in this video I'm going to discuss about the theories of failure, that is maximum shear stress theory. In the previous video we have discussed about the maximum principal stress theory, so do subscribe for the upcoming videos of machine design. So first of all, let me tell you one thing. The maximum shear stress theory is applicable for the ductile material, and the maximum principal stress theory, which we have discussed in the previous video, is applicable for the brittle material. Okay, so every failure theory is having its own statement. The statement of maximum shear stress theory is: the failure of a mechanical component subjected to biaxial or triaxial stress occurs when the maximum shear stress at any point in the component becomes equal to the maximum shear stress in the standard specimen of the tension test when yielding starts. Okay, so according to the statement, first of all, I'm going to construct the Mohr circle, okay, which we have seen in the previous video. Okay, so here you can see the Mohr circle. So according to the principal stresses, maximum principal stress is sigma 1 is equals to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 bracket square plus tau square xy. Minimum principal stress sigma 2 is equals to sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 bracket square plus tau square xy. And maximum shear stress is tau max is equals to plus minus root of sigma x minus sigma y by 2 bracket square plus tau square xy. So here you can see that actually the maximum shear stress is the radius of this circle. Okay, so according to the statement, what the theory states: the failure of a mechanical component subjected to biaxial or triaxial state of stress occurs when the maximum shear stress induced in that component becomes equal to maximum shear stress induced in the standard component under tensile testing. Okay, but as we know that during tensile test only one uniaxial type of stress is there, which is called as a tensile stress. And so according to that, in tension test the specimen is subjected to only uniaxial stress. So here you can see that in that case sigma x, which is the stress, normal stress, which is I have plotted on the x-axis, it will be equals to sigma t. And as we know that in the standard tensile strength testing, the ductile material failure of ductile material starts at yield point, which is called as SYT, which is also called as yield strength in tension. Okay, and the remaining stresses, as in the standard tensile testing process, the component is subjected to uniaxial type of stress. That means the remaining stresses, that is sigma y and tau xy, will be 0 because it is the uniaxial condition. So here sigma y will be 0 and tau xy will be 0. When I will put the value of sigma y and tau xy in equation of sigma 1, that is maximum principal stress, the equation becomes sigma 1 is equals to sigma x plus 0 by 2, because in the standard tensile testing procedure remaining two stresses are 0 because the test is uniaxial stress. Actually the component is subjected to uniaxial type of loading. Okay, and also tau will be 0. Then the equation will be sigma 1 equals to sigma x by 2 plus root of sigma x by 2 bracket square. Okay, so it will be sigma x by 2 plus sigma x by 2. It means sigma 1 will be equals to sigma x, and here sigma x is nothing but it is SYT, that is yield strength in tension. So it means that according to the maximum shear stress theory, when sigma y and tau xy will be 0, maximum principal stress will be equals to yield strength in tension. Okay, next similarly I am going to put the value of sigma y and tau xy in the equation of sigma 2, that is the minimum principal stress, and tau max also. So here you can see that when I will put the value of sigma y is equals to 0 in the equation of sigma 2, it will be sigma x by 2 minus root of sigma x by 2 bracket square. So it will be sigma x by 2 minus sigma x by 2, it will be 0. So the value of sigma 2 will be 0. Okay, and similarly when I will put the value of sigma y and tau xy in the equation of tau max, that is maximum shear stress, the equation will be tau max is equals to plus minus root of sigma x minus 0, because sigma y is 0 by 2 bracket square, and tau square xy is also 0, tau xy is 0. So it will be tau max is equals to sigma x by 2. And already according to the statement of maximum shear stress theory, the sigma x, the value of sigma x is actually SYT. So it will be tau max is equals to SYT by 2. So here you can see that the maximum shear stress induced in the component is half of the maximum principal stress. Okay, so or it is the half of the yield strength in tension. Okay, so here mathematically we have seen that how the maximum shear stress is actually half of the maximum principal stress, or it is the half of the yield strength in tension of the material which is under tensile testing. So it means that when a component is subjected to biaxial or triaxial state of stress, the failure of a component under maximum shear stress theory will be tau max will be equals to tau max, the value of tau max will be equals to half of the yield strength in tension of that material, value of yield strength in tension of that material. Okay, similarly if you'll take a look in the Mohr circle, as here we have proved that sigma 2 will be 0, then the value of sigma, when the value of sigma 2 will be 0, the circle is going to pass through the origin. Okay, because sigma y, for the value of sigma y is equals to 0 and tau y xy is equals to 0, when I will draw a circle, it will pass through the origin. Okay, so let us see. So here this is the figure of triaxial state of stress, and according to the maximum shear stress theory, the figure will be like this, because as we have proved that sigma 2 is equals to 0, the circle will pass through the origin, and as already we have derived that the radius of the circle is nothing but it is the maximum shear stress. So here the radius of circle is tau max, and the maximum principal stress is sigma 1, which is represented on the x-axis. So here diameter of circle is the sigma 1 and radius of circle is the tau max, and tau max is the half of the sigma 1. So tau max will be equals to sigma 1 by 2, and already we have proved that sigma 1 is equals to SYT. Okay, so when the specimen starts yielding under tensile testing, sigma 1 will be equals to SYT, so tau max will be equals to SYT by 2. Okay, so tau max is nothing but it is the maximum shear stress induced in the component. Basically this theory is applicable to only ductile materials, because ductile materials are weak in shear. So therefore the maximum shear stress theory predicts that the yield strength in shear is half of the yield strength in tension, that is SSY, that is yield strength in shear, is equals to 0.5 SYT, that is yield strength in tension. Next I'm going to plot the shape region. So suppose sigma 1, sigma 2 and sigma 3 are the three principal stresses at a point on the component. The shear stress on the three different planes are given by here the sigma 1, sigma 2 and sigma 3 are the three principal stresses acting at a point on the component. Okay, so the shear stress on the three different planes, here we are going to calculate the tau 1 2, that is the shear stress acting on tau 1 2, which will be equals to sigma 1 minus sigma 2 by 2. Similarly tau 2 3 will be equals to sigma 2 minus sigma 3 by 2, and similarly tau 3 1 will be equals to sigma 3 minus sigma 1 by 2. So this is equation 1. Okay, similarly the largest of these stresses, I'm going to largest of these stresses equate to tau max. It means that I'm going to equate the tau max to the largest of these three stresses, or SYT by 2. So considering the factor of safety, sigma 1 minus sigma 2 by 2 is equals to SYT divided by 2 into factor of safety. Okay, or The same equation can be written as sigma 1 minus sigma 2 is equals to SYT divided by factor of safety. Here SYT is the yield strength in tension, and as we have discussed that the maximum shear stress is the half of the yield stress in tension. Similarly, sigma 2 minus sigma 3 will be equals to SYT divided by factor of safety. Similarly, sigma 3 minus sigma 1 will be equals to SYT, that is yield strength in tension, divided by factor of safety. So the above relationships are used to determine the dimensions of the component. Okay, so here we are going to refer the expression 1 against equating the largest shear stress tau max to SYT by 2. Okay, so sigma 1 minus sigma 2 by 2 is equals to SYT divided by 2, or the equation can be written as sigma 1 minus sigma 2 is equals to SYT. Similarly, this is equation number 2. Similarly, sigma 2 minus sigma 3 will be equals to SYT, and sigma 3 minus sigma 1 will be again equals to SYT, and this is equation number 4. Okay, so here for compressive stresses, as I have already discussed in the previous video of maximum principal stress, here I am going to assume that the yield strength in tension is equals to yield strength in compression. Okay, so according to that, sigma 1 minus sigma 2 will be equals to when yield strength will be yield strength in tension. I have assumed that here the yield strength in tension is equals to yield strength in compression. So the equation will be sigma 1 minus sigma 2 is equals to SYC, that is yield strength in compression. Similarly, sigma 2 minus sigma 3 is equals to SYC, and sigma 3 minus sigma 1 is equals to yield strength in compression. Okay, so here we have assumed that SYC, that is yield strength in compression, is equals to yield strength in tension. The same equation can be written as sigma 1 minus sigma 2 is equals to plus minus SYT. Here positive symbol or positive sign represents the yield strength in tension, and negative sign represents the yield strength in compression. Okay, similarly, sigma 2 minus sigma 3 will be equals to plus minus SYT, and sigma 3 minus sigma 1 is equals to plus minus SYT. Once again, I am going to repeat that positive sign represents the tensile stress, and negative sign represents the compressive stress. Okay, and for the yield strength in compression, and we have considered that, or we have assumed that yield strength in compression is equals to yield strength in tension. Okay, so here I am going to plot the safe area. Okay, so here to plot the region of safety for biaxial stresses, already we have discussed about the triaxial stresses. So here I am going to assume that sigma 3 is equals to 0 for the biaxial stresses. The above equation can be written as sigma 1 minus sigma 2 is equals to plus minus SYT, that is yield strength in tension, plus similarly sigma 2 will be equals to plus minus SYT, because sigma 3 is 0. Okay, and sigma 1 is equals to plus minus SYT. The construction of region of safety is illustrated in figure. Okay, in this figure I am going to plot a figure to construct the region of safety according to the maximum shear stress theory. So here on the x-axis I am going to plot the maximum principal stress, and the y-axis I am going to plot the minimum principal stress, that is sigma 2. Okay, so here I am going to tensile stresses are considered as positive, while compressive stresses are considered as negative. So first of all I am going to draw two axes. Horizontal axis represents the maximum principal stress sigma 1. Vertical axis is sigma 2. Okay, to the right side of origin I have considered the positive stress, to the left side of the origin I have considered the negative stress, and similarly the stresses which are having direction towards the upward side, or on the y-axis, positive y-axis, I have considered the tensile stress, that is positive stress, and on the negative y-axis I have considered the compressive stress, that is negative sigma 2. Okay, so first here we have assumed that the sigma 1 is equals to plus syt and sigma 2 is equals to plus syt. So let me plot this on the x-axis. So this is the plus syt and this is the plus syt for the y-axis. Okay, for the sigma 2 is equals to plus syt and sigma 1 is equals to plus syt. Similarly, for the value of sigma 1 is equals to minus syt. Minus syt means yield strength in compression. Okay, it will be towards the left side on the x-axis, and on the y-axis it will be at the below the origin. Okay, so this is the region. So I'm going to draw the vertical and horizontal lines from every point. Okay, so this is the line, vertical line, this one is the horizontal line. So I'm going to assign the names. To this point I will call as A, this is B, and this is C. Similarly, for the third quadrant, okay, here you can see that again for the third quadrant, two values of compressive stresses are there. So for the sigma 1 minus syt and for the sigma 2 minus syt, that is yield strength in compression. Okay, so let me draw a vertical line from this point, and from this point I am going to draw a horizontal line. So at the intersection point, okay, so I'm going to assign the names D, E, F. Okay, so for the remaining quadrants, for the quadrant second quadrant and third quadrant, I'm going to directly connect this point CD and AF. Okay, which is going to represent the sigma x, sigma 1 minus sigma 2 is equals to plus syt. So this is the sigma 1 minus sigma 2 is equals to plus syt, and this is the sigma 1 minus sigma 2 is equals to, sorry, this is minus syt and this is the plus syt. Okay, so here you can see that this is the region inside which there will be the component will be safe, or there will not be any kind of fear due to shear, due to the maximum shear stress. Okay, but beyond this, along the x-axis, if the stress is going to, yield stress or the maximum shear stress tau max is going to exceed the point A or the point D or the point C or the point F, the component is going to fail. So this is the area of the hexagon A, B, C, D, E, F is the region of safety. Okay, thank you.